If you're building a machine learning model for classification, what is a metric that you'll use to evaluate how well your model performs classification on your test data? Just like with regression, you can also perform classification tasks using a deep neural network in TensorFlow using an estimator for this, the DNN classifier. In this demo, we are going to use another popular dataset for machine learning problems, the iris dataset. Iris is a kind of flower, and we are going to predict the kind of iris flower based on the length and width of the petals and the sepals. The original source code for this is available on the TensorFlow website. I usually clean up the code a fair bit and simplify it so that you can follow along. Here are all the imports for this particular problem. They're no different from what we saw for the regression algorithms that we coded up earlier. We may not use all of these libraries here, but it's just useful to have them all in there. The IRIS dataset is also available at the University of Chicago's machine learning databases. Like I said, this is a huge repository and has a bunch of interesting datasets, the IRIS dataset amongst them. I'm choosing to download this dataset from the TensorFlow website, though download.tensorflow.org, and there are CSV files for the training data and a CSV file for the test data. I'm going to store the downloaded file in the current working directory, call it iris underscore training.csv and iris underscore test.csv. Once again, we've automated the download function by using a helper function called download underscore data. If the file doesn't already exist on your local machine, it'll make a URL request to the training as well as the test path URL in order to download and store the CSV file on your local machine. We'll print out messages of success once the download has been completed successfully. Download the data and verify that it's present in your current working directory. There you can see it, iris underscore test.csv, iris underscore training.csv. We are now ready to load this data and get working on our machine learning model. The input features to our deep neural network classification model are much simpler this time around. We simply have the sepal length and width and the petal length and width expressed in centimeters. The labels associated with each record is an integer which represents whether the flower is of type Iris centosa, Iris versicolor, or Iris virginica. The labels are integer values 0, 1, and 2, representing each of these types of iris flowers. In this example, we won't be using pandas data frames to read in and store the data. Instead, we'll use the dataset API from TensorFlow. Now, the dataset API reads a record at a time, and we're going to parse a single line at a time and extract the values from the CSV file. This is our parse underscore CSV helper function. The only argument is an input line present in the string format on which we call tf.decode CSV to extract the column values. The tf.decode CSV library function expects a tensor of type string. The second argument to this function are the record defaults, the default values for a single record. These default values essentially indicate that the features are floats, that is, the first four fields are floating points, and the label is an integer represented by 0. The label is the last column in our CSV data. The tf.decode underscore CSV returns a list of tensor objects. Extract the label from that tensor. The label is the last tensor, the last column in our CSV data. Once we've extracted the label, we can go ahead and delete it from the parsed underscore line tensor. We no longer need it to be part of our feature set. Return the features in dictionary format. So we form a dictionary by zipping up the feature names and the parsed line. This will essentially give us the dictionary where the keys of the resultant dictionary are the feature names and the values corresponding to those keys are our feature values, the sepal length, petal length, and so on. Return the features and the labels from this helper function. Remember that this is for one record, one line in our CSV. Let's write another helper function to read in our CSV file and extract the features and labels. This takes in arguments such as whether we want to shuffle the data set and whether we want to repeat the records in that data set more than once. If you want training to run for multiple epochs, one way to specify this is to basically repeat each record in your data set, say n times, if you want training to run for n epochs. Each record will be present n times and will be seen n times, which is equal to passing through the dataset n times. Here we'll read in the CSV file using the dataset API in TensorFlow. A dataset in TensorFlow represents a sequence of elements where every element can contain one or more tensor objects. The text line dataset deals with text elements. Once you've extracted the elements into a dataset, you'll use an iterator to access them. While reading in our CSV data for our iris flowers, we want to skip the header row. So we specify skip 1. Every text record here is a string which has column values separated by commas. We pass in the parse underscore CSV helper function that we set up earlier in order to extract the features and labels and store it within our dataset. If you're using a data set for training, it's good practice to shuffle the data so that the records are not present in any pattern which the machine learning model inadvertently picks up. So if you've specified shuffle is equal to true, you can call dataset.shuffle. Specifying a buffer size which is larger than the dataset size makes your shuffle more thorough. There are other useful methods that dataset offers. You can simply say dataset.repeat and pass in a repeat count. It'll automatically make as many copies of the data as you specify. We'll use a batch size of 32 here. This means when we use an iterator over the dataset, it'll return features and labels in batches of 32. There are a variety of different iterators that you can use with a dataset. The simplest of these is the one-shot iterator. This iterates over the entire dataset exactly once. Because we use a one-shot iterator, that is why we need to specify a repeat count. The repeat count allows you to specify multiple epochs in your training by using this one-shot iterator, which iterates over the dataset exactly once. And if you call iterator.getNext, it returns one batch of features and the corresponding labels. Remember, our batch size here is 32. Use this helper function getFeaturesLabels to extract one batch of features and one batch of labels from our training dataset. We'll explore to see how the batch features and labels look. Batch features is essentially a dictionary where the feature names are the keys and the values are basically tensor iterators, not a tensor directly, but an iterator over a tensor. Batch labels are also an iterator over a tensor which has a shape question mark, that is for the batch size, comma 1. The label associated with every record has a dimensionality of 1. Every column here in our input features is numeric and is continuous. So setting up the feature columns for our estimator is very straightforward. Each column is a numeric column. Instantiate the estimator for our classifier model, which is the tf.estimator.dnn classifier, which stands for Deep Neural Network Classifier. The feature columns specifies the metadata information for the features that we're going to pass in. The hidden units determines how many layers our neural network is going to have and how many neurons within each layer. We have 2 layers with 10 neurons in each layer. The n underscore classes specifies the number of output predicted labels because there are 3 types of iris flowers. N underscore classes is equal to 3. Like we've done earlier, call classifier model.train to start the training process of this classification model. Pass in the input function, which is the downloaded file name for training data. We want to shuffle this data, and our repeat count is 20, indicating that we want to make 20 passes over our entire data set. Our number of epochs is essentially 20. Once the training process for the model is complete, we call model.evaluate and pass in the test data. This is to determine how well our model performs. We pass in the test file name, shuffle is equal to false, and repeat count is 4. This is because our test data is kind of small. We just repeat it 4 times to get a reasonably sized data set. Store the results of the evaluation in the results variable, and when you iterate over the keys of results, you'll find one of the metrics that is displayed for a classifier is the accuracy. And you can see that the accuracy here is pretty good. It's at 93.3%. Let's use our test data and make predictions for the kind of iris flowers that the test data represents. We'll store the result in predict underscore results. Extract the predicted classes from our predict underscore results. We iterate over them, find the prediction object, and within the prediction object, we find the class IDs to find the predicted classes. In order to get a side by side comparison of our predicted classes with the actual labels for the iris flowers, let's read in our test file using pandas into a data frame. The columns that we want to read in from the CSV file are the feature names and the corresponding labels. And we want to skip the header row. That's why skip rows is equal to 1. Assign our predictions to the predicted labels column and then basically print out the data frame and see how the actual labels compare against the predicted labels. Like I said before, the test data set is rather small. We only got 2 labels wrong out of the set of 29. Only 2 labels were misclassified by our DNN classifier. Let's see if we can perform a little better. We'll use a deeper neural network with more neurons per layer and 3 layers, 16, 12, and 16 neurons per layer. And now just step through the code and let's see what the accuracy is. It has shot up to 96.66%, which means we've got just one predicted label wrong. Last time we'd got 2 labels wrong. Here we've got just one label wrong. The most common metric used for evaluating classification models is the accuracy. The accuracy is basically a measure of how many predicted labels were equal to the actual labels in our test dataset. A high accuracy means that our model got a large number of the classifications right.